Look at how most organizations try to process cash. They treat it like the system on the left, a rigid gear mechanism where every inbound payment has a perfect, predetermined invoice waiting for it. This is the legacy accounting view. You open a traditional enterprise resource planning system, an ERP, look at an open receivable, and assume the cash receipt will cleanly map directly to it, one-to-one. But at the enterprise scale, that strict logic shatters. Payments arrive with noisy data, remittance references are missing entirely, and customers short pay, combine dozens of invoices into wires, and cross currencies without warning. Cash application requires a convergence of specific disciplines: statistics, search optimization, and graph theory. You are managing a high-velocity stream of incomplete datasets, where the objective is to resolve ambiguity through math rather than manual entry. To make sense of that chaos, you have to stop searching for perfect text strings. You must rely on graph theory to map entity relationships, probability to weigh options, and search optimization to evaluate millions of potential permutations. These are tasks designed for artificial intelligence, not static ledgers. Because cash application is an information discovery problem, it cannot be solved inside the rigid confines of an ERP. It has to be completely decoupled, and this requires a totally new structural framework. As you see in this diagram, we separate the logic from the monolithic core into 4 independent vectors. We call this a BAIC independent architecture, meaning the system operates entirely independent of the specific business, ERP, industry, or country. By pulling the matching logic out of those 4 constraints, the mathematical operations are no longer throttled by how a specific software vendor organizes its database. This universal decoupled framework is executed natively on Bayflex.com. When you strip away localized accounting regulations and rigid ERP field limits, probabilistic AI models can operate purely on the mathematical reality of the financial data streams. Once decoupled, the engine focuses on a single objective: the continuous reduction of financial uncertainty. This chart maps the match confidence spectrum. Here, at the 0% mark, we have a $9,850 payment with missing references. The system has to move this data point as close to 100% certainty as possible. It begins by applying Bayes' theorem. The engine calculates a prior probability by analyzing the customer's historical payment behavior, establishing an initial statistical baseline. Next, it measures numerical distance. It scans the open ledger to see how closely the $9,850 aligns with various combinations of open invoices, pushing the confidence score higher. It then runs entity similarity algorithms, executing fuzzy matching on the customer name and banking metadata to add further statistical weight. Finally, it calculates text probability. It pulls optical character recognition data from the raw remittance advice, matching those extracted strings against the ledger to cross the threshold of certainty. If the final accumulated score lands between 95 and 100%, the system triggers straight-through processing, or STP, clearing the invoice automatically without human intervention. The algorithm does not look for a perfect binary match. It calculates the highest statistically justifiable probability to automate the settlement. Executing Bayes' theorem across millions of invoices at enterprise speed requires a highly structured data environment. Flat ERP files are too slow and brittle for this volume of calculation. This isometric model shows how Bayflex.com structures the environment. It stacks the ecosystem into 3 distinct geometric planes, separating the data into isolated domains. The base layer is master data, or MD, Cash App. This contains the universal entities, like customer hierarchies and internal bank rules, that define the playing field. The middle layer is activity data, or AD, Cash App. This holds the raw transactional truth of the actual inbound cash receipts and the open subledger liabilities. The top layer is logics data, or LD Cash App. This is where the AI models, fuzzy matching heuristics, and tolerance thresholds live. Organizing these domains into distinct, isolated tables allows the AI engine to scale universally across any global enterprise without fracturing. But probability relies on evidence, and sometimes the evidence is too weak. If a payment's confidence score lands in the ambiguous 50 to 80% tier, the AI pauses. This is where the system routes the transaction to the DCID Cash App, the Context Intelligence Engine. This interface uses the DView strategy, Instead of a dense legacy form, the user sees this split-pane canvas. On the left, exact OCR text highlights. On the right, dynamic AI-recommended invoices with clear confidence bars. It surfaces only the context necessary to make a decision. A human specialist reviews this highly contextualized evidence and clicks Accept Match. That single click instantly routes the data back down to the LD Cash App algorithms through a machine learning feedback loop. Every functional human decision acts as vital training data. The system vectorizes that institutional knowledge, adjusting its own weights to improve future AI accuracy and drive up straight-through processing rates. If you look closely at how the Bayflex.com ecosystem operates, you realize that the architecture treats every component, from customer records to machine learning weights, as a table. These tables function as the machine-readable DNA of the environment. Every row in the MD, AD, and LD tables provides the specific parameters the AI needs to execute a settlement. They are structural logic primitives. They act as the actual, readable instructions for the software itself. To process these primitives, the architecture relies on this central node, the TableFlex.ai table OS. Watch as the geometric planes of the MD, AD, and LD tables are drawn directly into the core. Table OS consumes these relational blueprints continuously, reading the exact specifications of the enterprise in real time. Using raw data structures themselves as the direct foundation for the software allows you to bypass traditional, rigid hard-coding entirely. Table OS operates in enterprise architecture the same way as C compiler operates in machine code. A traditional C compiler abstracts complex hardware logic, allowing humans to build software seamlessly, without writing binary instructions. Table OS mirrors this exact process. It instantly translates those static tabular matrices into a living, dynamic nodal web, a fully operational Bayflex.com software application. The speed of this instantiation means entire customized environments are rendered directly from compiled tables in seconds. By compiling these tables into live workflows, the system moves past the limits of binary accounting. It treats every transaction as a probability to be solved, allowing the engine to settle payments at a speed that static ledgers cannot replicate. By utilizing Table OS as a universal compiler, Bayflex.com empowers enterprises to rapidly deploy, govern, and customize an infinite number of highly complex financial realities.